Okay, so as I was saying, it is would be a shame if you don't see as early as possible functions of more than one variable, because it's really not a typical situation when you have only one function of one variable. Now you probably can think of examples. Function of more than one variable, anyone? Well, where's the function? Well, yeah, so I see what you're saying, and there is certainly a point there, but say 1. Okay, so it's a circle indeed, and there are two variables present, but those are the same variables as we always talk. What this is, as opposed to y is equal to x squared, these are actually quite an important point here to be made. If I could just as well take a minute to talk about it. The difference, what is the difference between these two?
Just the position of the variables.
Okay, yeah, but there is a more crucial difference.
One's quadratic and one's not.
Well, they're both kind of quadratic, I suppose. Well, you can just think about how much time we spend on the first one and how little on the second. Not that crucial. The difference is one is a function and the other one is not. So this is a function of one variable. Y depends on x, and this is not a function. It's an equation, and you can all equations with the same variables. It's x and y in the first line, and x and y in the second line, right? So it seems about the same thing, but the difference is that y is not expressed explicitly or directly in terms of x. So that's why it's not a function. Even though behind every equation of this kind what there is the relation between x and y. It is just implicit. Okay, it is also a relation that might not be necessarily a function because it will violate the vertical line test. Okay, so but that is really actually a secondary problem. The real problem is that it's very hard to study relations that are given implicitly as this, in spite of that thing that we did in related rates and implicit differentiation. So you can differentiate the second one and extract some information about it, but really if a relation, we're talking about a relation between x and y, there is really no substitute for the first one. Even if you just try to plot it, you only know that this is a circle because you have seen it. But if I change it slightly and then yeah, well, no, maybe not slightly. That doesn't matter how I don't know what this is. I mean, it's very easy to change the equation, and then the plotting of such a relation will be virtually impossible. You cannot plot it point by point, but rather, well, imagine what would you plot? How you plot the first one is very clear. It is a table of values, x's and y's. For each x, you pick a bunch of x's, you compute a bunch of y's, right? We did it a while ago, right? How do you plot the second one?
We know that the radius is going to be 1.
No, but once again, you're using information that it is a circle. But if you don't know that it is a circle, how do you plot it? Well, like this one. It's not a circle. So you want to plot it to understand the relation, and yet, so how?
You got to get y by itself. And then
Impossible. Look at it. You cannot solve it for y. It just cannot be done. It is actually more exception than a rule that you can just look at the equation and solve it for one of the variables. So the challenge is actually what you end up doing is at best you check you gotta plot all x y's that satisfy the equation. Okay, that's what plotting is. And it's once again, it's very easy when you have an explicit formula, because for each x you'll have y, and in each row you will get a point. As many x's you pick, for each one of them will have a y and you have a point, and you have 100 computations, you will have 100 points. With this one, it's not so easy, because you're going to do what? There is nothing but trial and error. There is no trial and error for functions, because, once again, every x, as long as the formula works, you get y, and you have 1 point. With the second one, you have to, I don't know, you try 0 and 0. I don't know, 0, well, I don't even know what that...
0 to the 0 power.
How about 1? I don't want to go into that discussion. How about 0 and 1? So then it will be 0 minus 0 is equal to 0. No, 0, 1 does not belong to this curve. So it's a curve, presumably, but 0, 1 does not belong to the curve. 0, 0 is even unclear because it's indeterminate. So that's, and then you keep checking, and then you will have more failures than successes. And so you could expect that it's for 100 points, to plot 100 points, you would expect to carry out like 10,000 computations in order to just plot 100 points. And even then, you will never be sure that you get it right. So that's why we always do this. If doing this, meaning convert this implicit relation to an explicit relation of function, if possible, and then that usually does the trick, if it is, but it's just sometimes not possible. So I guess that was a little bit of an starting point of our review, because it's a very important point in calculus, explicit versus implicit. Because what are we studying? We're really not studying the second one, because it's just so hard. And but the functions, when there is an input, there is an output, and for every input taken from the domain, we will get the output. So it's very straightforward, and that's why it can be studied with the means that we've got. And the second function is that just we do it as much as the second non-function. We only can do it as much as we can, as much as we can convert implicit relations to explicit. So once again, this is implicit, and this is explicit. And, explicit is always better than implicit, obviously. And if you can convert implicit to explicit, then you do it. If not, then you're pretty much stuck. Anyway, the point being, but by the way, the curves, that you see it in calculus too, that there are better ways to describe curves, even those that violate the vertical line test, than implicit curves. There are better ways. But the point I was making is a function of several variables. If you look at this one, this is what we mean by several variables. Is say maybe x, y, and z, or x, well, I guess this is the typical example where you have 2 inputs and 1 output. Okay, so look at it. Y equals x squared, 1 input, 1 output, and that's why you have a table with one column for input and 1 column for output. And now what we end up with is 2 inputs, sort of, and 1 output. So that is, it seems to be a challenge, but I just wonder, you probably can think of examples, and better you do it now, of functions in, say, anybody's taking physics class, functions, or any kind of class, functions of 2 variables or more, anything. I'm sure you do. It just wasn't named this way. Some quantity depends on 2 other quantities.
Force equals mass times acceleration.
Well, why not? Even though force is time. Okay, why not? Okay, so as you can see, then we would have these as 2 input variables, and this is 1 output variable. That example algebraically is certainly fully applicable, and that's an example of one function. I could do, for example, if I really, there's a problem with the physics, but mathematically there is no problem. I could differentiate with respect to m, and I have a. I could differentiate with respect to acceleration, and I will get m. Okay, so that works out just fine. The problem is with the physics, because it actually assumes, what does it, it assumes constant mass pretty much. If the mass is not constant, then this formula doesn't work. So for example, a rocket, as it goes into space, it throws what? The pretty much fuel backwards, and so it loses weight. So that's not going to work anymore. So from the point of view of physics, it's not entirely applicable. But maybe pressure, as it depends on what could it depend on?
Surface area.
Okay. Well, once again, let's physics. How about pressure versus volume versus temperature? Does it look familiar?
PV equals nRT.
PV is equal to what?
nRT.
N capital, is it?
No, it's lowercase. It's moles, number of moles times the R constant.
R constant and
Times
temperature.
temperature.
Well, okay, that close enough. Okay, so you certainly can imagine that there's a bunch of formulas in physics like that, and all of them establish relations between the variables, as long as mathematically we have to assume that they are, if we want to build a function from it, we will have to make sure that those variables are input variables will be independent. For example, if I want to speak of the pressure as a function of, as I try to indicate here, as a function of volume and temperature. Okay, so what do I have to do? I have to make sure that the change in volume does not change the temperature, and change in temperature does not change the volume. So if I have control over those two variables independently, then you have a function of two independent variables. So as would be n r, these are just constant numbers, t over v. Okay, so once again, that would be a function. I would write p of tv is equal to n r t over v, and that would be a function of two variables. So once again, it is possible. You can set up your experiment in such a way that some kind of closed chamber, and the volume is either fixed or you can change its size, but it's totally under your control. And the temperature also, you change the temperature at will. So if that is your setup, then you can say that the pressure depends on temperature and volume as a function of two variables. Okay? So once again, the independence of those variables of each other and of the output is crucial. So if you are setting up some kind of in more natural circumstances, maybe you have a balloon and you heating it up, everything will be changing simultaneously. So even though you might be able to change the temperature, but it will affect simultaneously the volume and the pressure. So somehow they might be changing at the same time because of the physics of the relation between them. So it's possible. But if you want to make sure that you sort of, there are 2 degrees of freedom, and they're fully independent of each other. So in this particular case, you should be able to change volume freely and the temperature freely without interfering with each other. Okay? So then it becomes a function. More typically, a function of 2 variables. More typically, you just it's really not complicated to think of it. It is just almost as good. Very frequently, it is when you just look at it as 2 functions. It's the same formula, but you can think of it as a function of one variable or the other separately. So I could just have the same formula like this. So the same formula, one variable, it depends on temperature, or it depends on the volume. Pressure depends on the temperature or the volume. Once again, as long as you have control over temperature, you have pressure, or you control over volume, you have pressure. Or you can actually flip everything upside down, and you have your pressure being the variable, the independent variable, and the temperature or volume being dependent variables. So the point being is that, of course, once you have this, then calculus 1 applies, because then you have the derivatives. And derivatives with respect to both of the variables. Right, so I want to know how fast the pressure changes relative to the change of temperature. Okay, so, and our formula will give you the answer, and the same for the volume. So that's typically how you look at functions of several variables, is when the two variables are pretty much independent of each other, and then calculus 1 applies in a pretty much independent manner with respect to each of the variables. You just do differentiation, integration, anything you want. However, there is one, so that's a typical way to look at functions of several variables. But what I started with is actually last time is different. So these, if we're talking about, say, the terrain, then there are two variables, but they're of the same nature. So you have, say, if you already have the Cartesian system set up, or just a map, you have one direction is north south, and the other one east west. So then these coordinates are nothing but a tool for determining your location. So in that sense, what you combine x and y into one variable. You probably a bad idea to combine temperature and volume into one variable, because they are so different in nature. It might be dependent. But x and y are certainly independent, and they're also, the whole setup should be independent of the map that we pick. So then that makes a challenge of developing a pretty much multi-dimensional calculus, which starts like late in calculus 2 and then continues in calculus 3. Then functions become, then the graphs look like this on left. So instead of curves, they become surfaces, and then you study those surfaces in the same manner. You want to know slopes, you want to know integrals, but instead of areas, you're computing volumes, and so on, so on, so on, so on. So that just a view, and there is really no way sticking with two variables. That's just never going to happen, because if you just think about motion, and that's some of your exercise about that motion, then you already have three variables. You have time, you have x and y, and location given by two numbers. The story is opposite to this, but you still have to deal with three variables to begin with. So more variables, more way to combine them, more types of functions. But I guess the main idea is the understanding of functions in the abstract manner, and that is input versus output. So the nature of input really doesn't matter, nor the nature of the output. They could be anything. Well, we had that discussion early on. Remember the Senate, what was it? Do you remember so the function would be the senators, the domain is the senators, and the range is the states. Okay, so the function that takes a senator, assign a state to him or her. Okay, so that would be function looking like this. So two arrows originating from every location. So that's what you should think of functions ultimately as a very abstract entities. And if you do, then this will be much easier to deal with as dimensions grow, and you can't think of numbers anymore. Location is not a number, for example, or combinations of all kinds of variables, also. At best, you can say there are a bunch of numbers, but ultimately, at some point, you will be it's more convenient to speak of, say, locations. A location on the plane is what your input is, and the output is the elevation is indicated there, and vice versa too. So maybe your input is time, and your output is location. So the opposite story, and that the only way to study motion is in that manner. And so point is not a number, unfortunately. So anyway, so every time you see a formula in physics, there at some point that comes up. Any formula, we looked at some, but probably you can think of any number. Well, I mean, take electricity, electromagnetism, or thermodynamics. They have a bunch of formulas. Even before you get to do any kind of calculus or other calculus-based physics with those you should probably think about every formula that as a function. There is or a bunch of functions there. So that formula that you gave me, so you can treat it as a function of several functions in a different manner, depending on which you based on the physics or maybe experiment that you're conducting, decide which one of them is an independent variable, which one is dependent variable, or maybe plural. So any other functions you can think of from physics, or anybody's taking economics maybe? Okay, well, but physics is certainly full of formulas. Anyway, okay, so that was a good way to start anyway, because this discussion is very important, and so it will come up. Several functions, a function of several variables, will only start to become crucial in calculus 3, not even in calculus 2. But this issue of what function is and what is an implicit function is, it is more like you don't even want to call it a function. So this explicit meaning function, implicit means relation. And relation is what's so special about relation versus function. There is you're not necessarily pointing out, you don't, which one is the dependent, which one is the independent variable. Right? So x squared plus y squared equal to 1. Which one first, which one second, we shouldn't assume. And in fact, so x squared is equal to y. Well, as you can see, it is explicit. What I meant to say is x is equal to y squared. It is explicit, but here x depends on y rather than y depends on x. So depending on the circumstances, you might actually choose to switch variables and declare y to be the independent variable. So as you can see, this looks awkward, but if you rotate it like this, remember, like this, make y vertical. Well, I'm sorry. This is x and y. I messed it up. X. This is x and this is y. So if you just flip them, then x becomes vertical, and you have a function which passes the vertical line test. So you never know ahead of time. Okay, so let's start with a review. I hope you will. It will be guided by, at least in part, by your concerns. So as we're gearing up for the final, it would be good to know what parts of the course still not quite well understood. But at least so if you have anything, just jump in at any time if you feel that something needs to be discussed more in more conceptual level, even though if you do see a problem in sample test or anything like that, we certainly can talk about it. Okay, so let me just go over the main topics, and so one is sequences, which it was the very first topic, and that becomes bigger in Calc 2 more than now, but we really have utilized sequences a lot. They are really very convenient tools for handling a number of issues. So number one was limits. So limits of sequences to begin with. If you want to understand limits of sequences is a good way to start. So, like an is equal to 1 over n converges to 0 as n goes to infinity. So if you want to deal with a definition of the limits of the limit of a sequence, then this is the simplest situation that is imaginable. So that, just to refresh your memory, it will be 1 over n is for any epsilon greater than 0. There is an n. capital such that 1 over n is less than epsilon for all n larger than n capital. So starting at some point of the sequence, the values are so small that they are less than that standard of closeness that we choose epsilon. Okay, so we want to be within 0.5. We can cut off the beginning of the sequence and look at the still infinite remaining. That's a good thing about sequences, that it doesn't matter how much you cut off in the beginning, you still have you're still left with infinitely many terms left. And then so from your sequence you cut out some piece, and then you are left with, and all of these have values less than 0.5. Okay, and then you do the same with epsilon is equal to 0.1, epsilon is equal to 0.01, and they all will produce the same result. You remove more and more of the head. Okay, so that's, I guess, the way to put it. So this is the head or the body of the sequence, and whatever is left is always called the tail. The tail is infinite. No matter how large the body is in the beginning, it is the tail as what we're interested in as far as the sequence is concerned. And you just look at whether this tail wiggles or not, or if that wiggling kind of disappears or dissipates as we're moving along towards its end. Well, there is no end because it's infinite, so it keeps going like this. But if the wiggling disappears, then it becomes indistinguishable from what? From the limit, and the limit is this. This is the limit, and so this is somewhere limit. So always remember that limit is a number. So this is y equals 0 is the limit once again. So y equals 0 is what we have described as asymptotes whenever we talk about functions, but with sequences things are way simpler because we can only go in one direction, and there is no kind of a complex behavior of you cannot, well, so we're not concerned with limits at points, for example, only at infinity. So cutting off a larger and larger part of the body, leaving smaller and smaller tail is what the essence of sequences is. So any questions about this? So can you solve a problem like this if instead of 1 over n you have some kind of other sequence?
Like 1 over sin x?
Oh, yeah, that would be tough. Well, that would be, well, what is the conclusion about that one? 1 over sine x? 1 over sine x or 1 over sine n? So 1 sine n. We're still looking at sequences. They are simpler. What's the limit?
0? Is it 0?
No. Without the fraction. What's the limit of sine n? What?
1.
No. What can you imagine what the graph looks like? Remember, sine looks like this. This is the sine function, and then we pick points on it. Not a lot, but enough to draw a conclusion.
No limit?
No limit. So no limit. And what about the reciprocal?
It probably doesn't have a limit either.
Right. No limit. It is not easy to demonstrate because the function is kind of complicated. So it's certainly not something to worry about as far as the final is concerned. But an example of a function that you can handle for either for showing that the limit does exist, that's 1 over n. Okay, so I almost demonstrated, but it actually you have to solve the problem once and for all. You have to point out what epsilon is. I'm sorry, not epsilon is, what n capital is. See, we're saying that there is, meaning that we can find it. as you might remember, n is equal to 1 over epsilon. So for any epsilon, I can find n in this fashion, and it solves the problem. Similarly, if you have 1 over n squared, well, it will be slightly different. So that this kind of a simple problems you should be able to handle. So that would be number one. But number two, what came up is the opposite: is the limit doesn't exist. And so once again, some of them are just too complicated in order to be able to demonstrate the non-existence of the limit. But some problems are simpler. What is the simplest limit there with simplest sequence with no limit?
X squared.
Square root of x.
Well, fair enough. I mean, if you mean n squared, then it is. But n squared goes to infinity. Okay, so it is. I suppose it is the simplest one. But what about the simplest bounded sequence with no limit?
Not the square root of n.
What?
Square root.
No, it's still square root of n also goes to infinity. So the example is of sine n is kind of complicated. There's a simpler one with a similar oscillating behavior. Not as similar, but a much simpler oscillating behavior.
A polynomial.
No, simpler. That oscillates like this. Okay, let me plot it for you. What is the sequence?
Cosine.
No. Simpler. This is 1, this is -1. What is this? Well, how do you get 1 and then -1 and then 1 again?
Anything to the 0 power?
Close? No, not
Because
close.
it could be negative. You could have a negative n to the 0 power.
Negative n?
To the 0 power.
No, the 0 power is always 1. No, it's not quite. Well, actually, how about this question? Remember what the recursive formula is? Also, let's review that. an plus 1 in terms of an, say. This would be a recursive formula. So the next element in the sequence is twice the previous one. So that's called geometric or exponential growth, which we just talked about recently, right? So that's a recursive formula. And so doubling bacteria or money or whatever during a period of time. Recursive. And it helps to sort of, if you have an idea for a sequence, it helps sometimes to start with a recursive formula, maybe, so that then you can, at least you have something to something tangible, and then you can find the nth term formula. These are all nth term formula. They're explicit. This one, in a way, is implicit. Even though you can compute everything, if you have the previous one, you'll find the next one. You can find all of them, sort of. But that's not what we are after here. Okay, so can you think of, if this is my sequence, what's its recursive formula? So A naught is equal to 1. How do I get, what's the difference?
Just negate it.
Negate, in other words, an plus 1. How do I negate algebraically?
Multiply by -1.
Multiply by -1, that's right. So this is actually the formula with the including the initial value of 1. This is the recursive formula. I just simply multiply the term by -1, and every time it will oscillate between -1 and 1. And so think about it then. this doesn't have a limit, right? Oscillates between -1 and 1. There is no accumulation towards one single value in a manner of. So one way to think about it doesn't matter how much of the body you cut away from the sequence, what's remaining will look exactly the same, and so there won't be any pattern appearing. That's roughly what the explanation is. Okay, so that is that's fine. Okay, now there is an nth term formula. You should know. Term formula. An is equal to what? So in other words, n-term formula means that an in terms of n, not in terms of an minus 1. So how do you make it alternate? Well, actually, I could try this. So a naught is equal to 1. A1 is equal to, I'm just using the formula. So it will be -1 times 1. A2 is equal to -1 times -1 times 1, right? A3 is -1 times -1 times -1 times 1. So an is what?
-1 to the n.
-1 to the n. Okay, that's it. So that's once again very, very crucial sequence that you need to know as an example for kind of the simplest example for somewhat complex behaviors. So one is they're just a bunch of very simple but very crucial examples that they will take you far. There is even a sequence. Well, there is some kind of saying that I can't remember exactly, which pretty much says that 10 examples are as good as a theorem. So if you have a few, you can cover a lot of material with nothing but several good examples. So good example is 1 over n, bounded sequence that diverges, but then there is this one say unbounded sequence that diverges to infinity. 1 over n is a sequence that is bounded, converges to 0. Another example would be, as you can see, the 1 over n, it doesn't reveal all the important types of behaviors. Why? It is too specific. It is decreasing. This one is decreasing, right? So 1 over n, small and small and small and smaller, and the pattern is kind of simple. What about the function that not decreases, but it approaches 0, but it's not decreasing? So once again, let me. An approaches 0, but not decreasing or increasing. Well, first of all, can you imagine that? How does it do it? Well, think a pendulum so it swings and then starts to die out. Very, very, very practical situation, as a matter of fact. So and then at the end, it will. I mean, technically or theoretically, it will never stop because not all the energy will dissipate. So it will be approaching the equilibrium, but never. Same with the spring, but never reaching it. So you can imagine that such a situation. So what does the graph look like? Can you think of a
heartbeat?
Heartbeat. That's right, heartbeat. I suppose. I don't know. The patient is about to die, I suppose. Okay.
Over a lifespan.
Oh, yeah. I suppose so. The heartbeat is declining, maybe. Well, anyway, okay. So the last question, and then what's the formula? So decline in the amplitude, we know how to do it. It's 1 over n. On the other hand, it oscillates. We also know how to do it right here. So what's the answer?
-1 over n.
negative 1 n over n. So oscillation over n. Okay, so we'll do some more reviewing next time.